Hi everyone. Today we're excited to have Dr. Shah Mohammad Bahauddin, a research faculty member working for the Laboratory of Atmospheric and Space Physics at the University of Colorado in Boulder. And he's speaking to us about his work on acoustic sources of the solar surface. So Shah received his PhD in physics from Rice University in Houston, Texas, and in 2019 was selected as a DKIST ambassador. So for today's seminar, he'll be presenting the quest for finding acoustic sources on the solar surface in the DKIST era. We're really excited to learn more about this topic, so thank you, Shah, and we're ready when you are.
Thank you so much, Emma. So hi, everyone, I'm Shah. So today I'll be presenting our work that we have been doing since last couple of years in preparation of the commission of Daniel K. Inouye Solar Telescope. I'm very excited to show you some of the interesting results that we might be able to find in next year. I can't show you any DKIST data at this moment. There are some embargo on the data. We need to wait for your publication. But here I'll be mostly talking about the analysis tool that we have developed so far, and what it would promise us to analyze the sun, right? Okay, so so if we look the sun in the Doppler, then what we see that there are tons of different flows that are constantly happening in our solar atmosphere and its surface. So we can see the rotational flow, and we can see that there is a signature of a differential rotation, and we can also see meridional flow components that are flows from pole to equator, right? And then we always see this convective blue shift, that is essentially there is an outward surface flow that is happening in our sun because of the pressure difference. And if we look at this convective blue shift, which means the outward pressure, we can clearly see that there is this convection that is happening in our sun, in our sun's surface, right? So you can think about the sun as some sort of a boiling plasma, right? So the convection currents of a plasma, they directly comes out through the photosphere, right? And sometimes they overshoot in the chromosphere. And what happens is essentially hot plasma is rising at the center of the granules, and the cooler plasma, they are getting sinked down through the edge of the granules that we call the intergranular lanes, right? So if you observe a relatively long time series of the solar surface, and then take a Fourier transformation, right? Then what you will find that there is actually two principal component where all the power is concentrated, right? So you will see over here, we have a relatively slow moving granulation. And on top, what we have here is the modal oscillations, or that which we call the P modes, right? The pressure modes. Now, if you take an image of the solar surface, a time series of the image, right? And then you filter it through this through the sound speed of the photosphere, then you can actually look at these two components separately, right? So this is what I have done over here. This is a Muron photosphere, and then what I have done is that I took a fast Fourier transformation of the image time series, and then took an azimuthal average, and then filter it out. And here, the middle image corresponds to the power of only this part. That means all the granules. And then on the top and on the right side is what corresponds to the power of this top part of this filtered power spectrum. Now, if I run this, you can easily see that our solar surface can be divided by two principal components. The first component, of course, the granulation, and the second component is due to the P modes. And we know that part of the P modes that are higher frequency, they can actually penetrate through the photosphere and they can make to the chromosphere and beyond, and they can deposit energy in the upper atmosphere. Now, the interesting thing that we are trying to find is that if you look at the right part of the animation, this is essentially P modes or the modal oscillations. That means they are normal modes, right? The question is, where do these normal modes come from, right? So in order to find that, we have to find individual acoustic sources, okay? So you can think this problem in terms of this. So here I have made another animation in order to explain it better. So suppose, think about it as a one-dimensional problem, right? So on top you have a guitar string, and then you can excite this guitar string at a random location at random times, right? So if you do that, then what is happening is that you are randomly exciting delta functions, right? But now if you look at the frequency space, that means below, then you will see something interesting, okay? So suppose we have individual excitations, right? And each of these individual excitations has mostly like a broad Gaussian spectrum in the Fourier space. But as time goes by, all of these individual excitation, they decay out, right? But only the resonant frequencies of their frequency distribution, they get to live. And over time, all of these resonant frequencies, they get to accumulate. And then if we go into long enough in the future or in a long enough time, you can see that we end up having this modal oscillation, right? So now on the top, the modal oscillations are the one that are dominating. But here, there is always these individual acoustic oscillations that are actually contributing into these modal oscillations, right? So our goal of this research is to find these individual acoustic oscillations and try to find out what are their characteristics, right? Because if we can find these individual acoustic sources, then we would be able to tell that why we have this kind of, P mode spectrum, or what kind of string do we have, or in terms, what kind of internal structure we have in the sun that is actually causing all of these acoustic sources and that is basically causing all of these P mode spectrum, right? So the target is to learn about these individual acoustic sources, not the modal oscillations, so that we can understand the nature of the modal oscillations. Okay, so just like I have shown you in the previous one, here, this part is coming from the modal oscillation, right? And this one is from the sunrise balloon flight, and this data was taken for something, I think, like 30 minutes or so. But if you take a long enough data, as for an example, years of data, then what will happen is that you will have a much better resolution in the Fourier spectrum. And we can do that using the Gong network, right? So it is continuously watching our sun. And by taking long amount of data, what we can find is that this is the spectrum of the P mode, right? Because here we have a much better resolution. We can see there are ridges, that means there are allowed mode that are more favorable to be excited on the sun, right? So in a sense, what we can say that our sun is like a bell that is struck by many tiny sand grains. So these individual sand grains, they are the individual acoustic sources. But over time, all of their contribution, they get decayed, except the ones that are resonant to the bell itself. And then what we see in our sun is that there is millions of oscillations, oscillation modes that are resonant to the solar interior, and they get to live. And we are seeing them as the P mode spectrum. Okay, so in this research, we were trying to find out that if we can find the contribution of these individual tiny sand grains or the acoustic sources. Okay. So how can individual acoustic source can be excited? So people have looked at it, scientists have been looking at it theoretically since 1990s, and they have found that there are several ways you can excite an acoustic source. So if you have a sudden fluid compression due to a pressure change, then you can have a monopolar excitation. Or if you have a little bit something more violent, like a buoyant acceleration in a stratified medium, then you can have a dipolar. Or if you have some sort of a fluctuating Reynolds stress, then you can have a quadrupolar excitation. So in terms of physics, if you have a local radiative cooling, right? Suppose you have a small granule that has suddenly done a little bit too much radiation, right? Then there will be a sudden cooling, and sudden cooling means there is a sudden pressure drop. And if you have a pressure drop, that means the fluid will get compressed, and you will have a monopolar excitation. Then you can have the fragmentation of a large granule, just like there can be like a groundbreaking during an earthquake or something like that. Or you can have an excitation within the intergranular lanes. That means two intergranular lanes, there can be a vortex and they can hit each other, and then there is an excitation. So these can actually do quadrupolar excitations, right? They are much more violent. Now, the thing is, if we want to find them in the observation, if we want to characterize them, so how can we do that? The answer is it's not that straightforward. Why? The reason is this, that when we look at the surface of the sun, we see there are two important contributions that has a majority of the power. The first one is, of course, the granules. They are kind of a laminar flow. They try to smooth everything, right? And then we have the P modes that are the resonant modes from the acoustic sources, right? They are the accumulated resonant modes. So the problem is these two are much more stronger compared to any individual acoustic source. Now, our target is to find these local acoustic sources. So what we have found that the problem of identifying this individual acoustic source is that the individual acoustic source is really weak in terms of this granular motion and the P modes. So here for this research, we have kind of designated all the granules and the P modes. They are like a background noise. They are really loud. They have 4 to 6 orders of magnitude, the higher amplitude perturbation. And our local acoustic source is a signal that is extremely weak. Okay, so you can think about it as something like you're trying to talk in a stadium and you're trying to find out that what individual person is you're trying to say, right? So it would be extremely difficult to hear, right? Okay, and then you can say that, okay, can't you do a Fourier filtering or something like that in order to take out all the contribution from the granules and the P modes? That's not so straightforward. And why? Because you remember the P modes, they were actually born from these local acoustic sources, right? So they actually shared their frequency components. So if you try to blindly filter out all the P modes, you will lose your significant power from the local acoustic sources as well. And so it has been pretty difficult to disentangle this the your local acoustic sources from this other your background noise. So what we did is that we thought that we need to do it not in the frequency space, but in the temporal space. And what we did is that we took help from a neural network. So we have developed a neural network that is capable of looking at this time series, and it was trained to look at a sample and tell if there is a wave or no wave. Okay, so the idea is that the neural networks are really good in finding patterns, right? And they will be able to, a convolution neural network will be able to efficiently filter out these contribution from the P modes, right? So our neural network could do it, and it would do with a reliably high efficiency, as for an example, like around 90% efficiency, not 90, I think 85 to 90% efficiency. But the more important thing is that we did not want to use the neural network as a black box, right? So what we wanted to do is to understand that what patterns the neural network is trying to pick out in order to filter out these images, right? So we tried to open up, so we have opened up the neural network. We have looked at each convolutional kernel. We tried to decipher that what it is trying to do. And we found something very interesting. So yeah, here it comes when you are trying to do explainable artificial intelligence, right? That you are not only using this as a black box, but you're trying to understand how it is doing it. So what we found is the neural network is not looking at the frequency space or the temporal space, but what it's trying to do is some sort of in the velocity space. Okay, so I'm not going to explain all the details at the moment because that would take a really long amount of time. But the basic idea is this, that if you look at the K omega diagram, you can see that you can draw this line in the K omega diagram, and any of this line, this actually corresponds to omega by K. That means a velocity, right? So this line corresponds to the velocity of the sound speed, on the photosphere. Now, everything below over here, which are essentially from granular motion, you can think about them as perturbations that are relatively slower compared to the sound speed, right? Now, suppose you are observing the sun, and you are observing the sun at such a fast cadence so that all of these perturbations that are due to granulation, they are oversampled, okay? And then if you take your difference image, then what will happen? So what will happen is that from one image to next, the perturbation is not moving at all because they are too slow, right? So if you take a difference image, they will cancel each other. And essentially what will happen is that all the granular contribution, you will find that you are not seeing them anymore. Now, you have you chose a cadence that is fast enough that it would oversample all the granular perturbation, but it needs to be slow enough so that it is all the contribution from the P mode that gets too fast, right? So if all the contribution from the P mode are too fast, then what will happen is that your observation will not be able to reconstruct all of this perturbation from the sample images, right? Now, again, if you take a difference image, and since you are undersampling it, that will also return you almost zero signal. So essentially what will happen is that all of the contribution from both the granule and from the P modes, they will get cancelled, except the perturbation that are actually moving at the sound speed, they will get to live. And anything that is moving at the speed of sound, we can say that this is because of acoustic sources. Now, there are some, other contribution that will come to later, but for now, we can safely assume that if we can filter out all the other things that were, except everything that is moving at the speed of sound, then we will be able to reliably find the acoustic sources, right? So this is what we have done. We have developed our own filter based on this understanding, and we have applied it in a simulated photosphere that we collected from a Muram simulation. And this is what it looks like. On the left, what we have is the line of sight velocity of the solar photosphere. And on the right is what we have is the filtered velocity, or what we call the residual velocity, that are moving at the speed of sound, right? So if we run this, we can see that the solar surface is actually full of all sorts of acoustic emissions. Now, here are two components that are important to understand. All of these bright white and black regions that you can see, these are not from the acoustic sources, okay? So these are actually from the edge of the granule where advective transport is happening, okay? And the problem is that the advective transport has a very close perturbation speed compared to the acoustic sources. So as for an example, acoustic source has a perturbation speed of like 7 kilometers per second to 8 kilometers per second. And these advective flows at the edge of the granules, their speed lies between 6.5 kilometers per second to 7.5 kilometers per second. And that is why our filter is still picking them up. It can't filter it out. But if you look in the middle, that means these areas, all of these perturbations that you can see, these are due to different kinds of acoustic emission, right? And here there is a strong one, which you can easily see. Here you will, if you can see my cursor, right? So when these two granules over here, they will hit each other, you will find that there is a strong acoustic emission. So as for an example, if you look over here, when this thing hit, you see there is an acoustic emission that is going out, right? And if you look at it for some time and you do it over time, you will be able to see that there are tons of acoustic emissions that are going out. So what we have developed is a way how we can see individual wavefronts. And by tracking these wavefronts, we will be able to find out the exact location of the sources, okay? Now, there is a third component that we also need to be careful, is what we call coherence patches. And these coherence patches come from this kind from P modes, and they can kind of fool you with the acoustic sources. They can fool you as representing the acoustic sources, but they have a specific time asymmetry that you can actually exploit, and you can understand that if this is actually coming from the P mode coherence patches, or they're actually from the acoustic source, right? So even after you get to see all of these acoustic wavefronts, you need to be careful. You need to look at case by case in order to make sure that this perturbation that is moving at the speed of sound, this is actually coming from individual acoustic sources. Okay, and now that we can see the individual acoustic wavefronts, so what can we do with it? So the first thing that we can do is that we can find out that, okay, the acoustic sources are over here, and they are very, very weak. So we can take azimuthal average in the atmosphere, and that would let us find the individual acoustic sources. right? We can characterize their amplitude. Then we can also characterize where they were born, right? And if we know the location of their of the source, then you can actually go to the atmosphere and look how the atmosphere was evolving and try to find out what is the physical origin of that source, right? And also from this analysis, you can also find out that of what is the speed of the source, right? Now you can one can assume that okay, the speed of the source is always going to be the sound speed of the photosphere, but that is actually not true. What we have found is that the source are not always born at the at the surface. They are usually born, most of the time they are actually born beneath the surface. Now we know that the photosphere, the upper convection zone, this is a stratified atmosphere. So that means if there is a sound wave that is coming through this upper convection zone or through the photosphere, it will be going through a gradient of density and pressure. That means the sound speed of the medium will be constantly changing, right? So when it will coming out through the photosphere, you will find that it is not coming out exactly at the speed of sound of the photosphere. What will happen is that you'll see there is some excess amount of speed. So how can we use that? So the basic idea is this, that when we will observe, what we observe is the surface velocity or the phase velocity of the acoustic source. And if we have a deep source or a shallow source, we can see that these two different location would cause a different source speed. Okay, so that means if you have a source that is coming through, if you have a source that is coming through an upflow, and that is relatively deeper, then it will have a very high wave velocity. Okay. Now, if you have another source that is coming through the same upflow, but that is actually much more shallower, then what will happen is that it will have a much less surface velocity, right? Now, if it goes through a downflow, then again it will have a different velocity. And also, if we look at the amplitude, that will also change differently based on how deep it is and what kind of atmosphere it is going through. So the important takeout is this, that when these wave fronts are coming out, they are going through all of this atmosphere, right? And they're coming from a definite depth. So when they come out, their wavefront shape has all of the information that it has been through the atmosphere and its own characteristics, right? So we can actually use this information, right? We can use the shape of the wavefront, how it is getting distorted, how its amplitude is changing, how its velocity is getting changed over space and time. And from that, we can infer the surrounding atmosphere, as well as the depth of the source and how the source went off. So here is an example. Suppose we have this a strong surface acoustic emission that is quite close to the surface. So for this particular one, this is a 100 kilometer deep acoustic source. And then you can see here that here is the acoustic source that is going off, right? So we can take this wavefront, and we can analyze how it is evolving with space and time, right? And from that, we can write an inversion code, okay? So the inversion code is still not fully functional, or it's not perfected. It's a very simple one that I have written very recently, but the result is very interesting. And if you see over here, so this is the actual atmosphere that we have. And from left to right, yeah, we are going through your depth, right? So this is like very close to the your surface, and this is almost 100 kilometer deep, right? And so this is the line of sight velocity of the mutant photosphere, and this is the inverted, which means we have inverted it from our observation of how this wave is propagating. And this is the inverted atmosphere, and this is the inverted line of sight velocity. Okay, and we can also guess the horizontal velocity and also the pressure perturbation, right? And you can see that when we go a deeper layer, the inversion starts to work worse, because over there we have less and less information, and the more the acoustic sources can interact with the atmosphere, the more data you have, right? And since this specific acoustic source was like 116 kilometer deep, we cannot use it to probe something below 100 kilometer. Okay, but it is very interesting that using just the shape of this wavefront, you can tell so much about what is happening deep in the photosphere, right? So I think the opacity minimum of the photosphere is about 20 kilometers, right? So you can see at best 20 kilometers below the photospheric surface using infrared. But with this technique, we believe we can probe up to like 100 kilometer or even 200 kilometer deep of the photosphere. That means we can first be able to see the convection zone with very high resolution details. Okay, and then there are more. You can do even something more, and is that you can do depth analysis. That means if you take these wavefronts at two different heights, then you'll be able to find out that exactly where it was born, right? And from that, you can also tell about the spatial structure of the atmosphere as well. And then we have also found that these acoustic sources, they don't come alone. So they are usually clustered. And if we go deeper into the photosphere, we see that there is a pattern. That means somewhere between 300 to 400 kilometer, these acoustic sources gets really, really loud, okay? And we have found this is very interesting because this is the height of, when we get to see this trans or supersonic downflows. And these downflows happen because here the hydrogen ionization reaches 50%. And because all of the energy is going to the ionization, so convection becomes really inefficient. And suddenly the flow drops, the entire plasma, they started to drop really fast. And that's why we see lots of supersonic downflows at this height. And if you suddenly have everything dropping, then all the flows that will come together, they will start to hit each other, and then you are supposed to see more acoustic sources, and that is what we exactly see, right? Okay, and then we have also seen that if we look at where these acoustic sources are happening on the surface, they have a spatial structure that would follow with a spatial structure that is 300 kilometer deep. So that means there seems to have some sort of a mesogranular scale of these events, right? So the question is, if we take account of all of these acoustic wavefronts, can we map everything that is happening between the surface to 300 kilometer? And that is what we are trying to find now. So that is a research on progress. And then we have also seen that there is also a temporal relationship. We have seen that when the acoustic sources come, it seems like this mesogranular layer that is 300 kilometer deep, that is actually driving all the acoustic sources, on the surface. But what we know is that solar granulation is usually being driven from the surface. That means causality goes from the top to the bottom, right? But here, what we are seeing, at least in terms of acoustic flows, that causality is going on the other way around, right? So I think there is a very interesting synergy between the radiative losses and the acoustic energy deposition, and there are so much we can learn if we can actually resolve them in the observation. And finally, all of this observation, we have made it in the simulation. Now it is time to go to observation, and now it is time to use DKIST and see them if this is really happening in the sun, or all of these are kind of a feature of the simulation, right? So the Muram simulation cannot generate supergranulation. So maybe this kind of mesogranular scale, or this kind of clustering that we see in the Muram simulation, this might not be present in the actual sun. So even if that is not present, then this actually tells us a lot about our limitation in the simulation, right? That how do we have to change our simulations so that they can better mimic the sun. So this is what we can say, and we can learn about whatever happening below the surface. But these acoustic sources, they also propagate upward, right? So we try to see if we can see them in the chromosphere as well. So when we took some Muram chromosphere, and we have looked at it, but now this is height-wise, we can also see that these acoustic sources, if you look over here, they are actually propagating. They are actually propagating on the top, and this dotted blue line, this is the photospheric surface, right? So the acoustic source was born right below the photosphere, and it is getting propagated upward into the chromosphere, right? Now, as it is going upward into the chromosphere, it is going through a higher sound speed atmosphere. So we had to adjust the filtration technique. So we did it for the first 500 kilometers or so, and after that, we did not do it anymore. But in practice, you should be able to do it, okay? So the thing that we can see that individual acoustic sources, their wavefronts, they propagate upwards, right, into the chromosphere. So the next question is, if there is a cluster of these acoustic sources, when they are propagating upward, how do they deposit their energy, right? So one way is that they can deposit the energy by producing shock, and the shock can also produce turbulence, and that can hit the surrounding atmosphere, as for example, the higher chromosphere or the lower transition region, or they can undergo mode conversion, and they can reach to the upper transition region or in the corona, and they can deposit energy through alpine wave, and they can even initiate the reconnection heating, right? So in order to see them, right, what we need is some sort of a multi-instrument capability that can be tuned to see simultaneously the photosphere and the chromosphere, and then the corona, right? And we need to have a very high spatial scale and the temporal scale. And if we have that, then we should be able to see that how local energy deposition and heating is happening in the upper atmosphere real time. And we would also be able to understand if this kind of acoustic sources or their power can be used for the acceleration of the solar wind. So I think that now we have, I think now we have the DKIST. We would be able to analyze these things in much more details, and we can use this analysis technique with its full capability. So far, what we have seen is that in order to successfully apply this technique, which means this kind of perturbation velocity-based filtering, you need to have at least 40 to 50 kilometers of spatial resolution and 2 to 5 seconds of temporal resolution. And in order to see their propagation through different layers of atmosphere, you need multi-instrument capabilities. Now, if you're able to do all of these things, then there is even more opportunity. So as for an example, people have been looking at phase difference maps of the photospheric and the chromospheric velocities, and they have shown that based on the magnetic field structure, you can look at how this acoustic acoustic power is changing, and from that you can infer what the magnetic field looks like. So now we don't have to rely only on the phase difference, but what we can do is that we can see how this individual wavefront is propagating through this magnetic atmosphere, and we can use them to diagnose the magnetic field itself, right? So this would give us an independent diagnostic tool for the magnetic field measurements in the quantum chromosphere. So we call it something like a magnetoseismology or a high resolution magnetoseismology. So people have done that before, but our technique would allow us to do it with a higher precision, with a higher resolution, right? So I think when DKIST will start to give us really good data, we'll be able to do all of this very soon. Now, in order to use DKIST, there is an observational challenge, and the observation challenge is this: that everything we have done so far, we have done it in the velocity space, right? Which means the line of sight velocity. But when you go and do observation, you don't do it in the velocity space, you do it in the spectral space. Now, can we see it in the spectrum? Now, the problem is again this, that we have so much noise from the granulation and also from the P modes. And our individual acoustic wavefronts, they are really tiny perturbations. So the problem is that almost all of the information that we have about these acoustic perturbations, they lies in the higher frequency region in both spatial and the temporal scale. Okay. Now, if we try to do this in the traditional way, that means we will first look at it. First, we will have a spectrum, and then we will invert it. Then we see that all of these high frequency components, they get lost. Okay, so you can't do it using inversion. What you have to do is that you need to do it directly on the spectrum itself. So we have tried to analyze this. We have tried to find out a way that how can we get it directly in the spectrum, right? Okay, so so what we have found that you need to look at the response function of the spectrum, and there you have to find a specific wavelength that has these conditions. Okay, so we need to find a wavelength that has the maximum power from the acoustic propagation, which means a wavelength that gets maximally affected by this small amount of velocity perturbation. And then the question is, every wavelength has a formation height, and the formation height it needs to be really narrow, so that any other contribution from any other your height cannot interfere. So we have developed a variable called alpha, and this your variable actually tries to maximize the effect of the acoustic your contribution on the velocity perturbation in the spectrum. And from that, we were able to find this this right your wavelength, this optimal your wavelength that can be directly used for imaging these acoustic perturbations. And you can see that since we only need one narrow wavelength, that means if we have a narrowband fast monochromatic imaging, then this should be more than enough to resolve the individual acoustic sources. So we have developed a technique that can find individual acoustic wavefronts. We have also seen that how you can use this technique to characterize the source and learn about the surrounding atmosphere. And we have developed an imaging technique that will exploit the spectrum itself in order to successfully image these wavefronts. So I think this will give us a very good opportunity to answer these long-standing questions. So as for an example, this will allow us to tell that if our real solar photosphere is bifurcated into loud and quiet regions, just like what we see in the Miriam simulation, or is it more stochastically distributed? And if it is, then why it is like that, and why, and where was Miriam is wrong, right? And then we can also learn about how deep we can map the upper convection zone with this kind of high resolution local helioseismic inversion, right? So for now, we assume that we should be able to do it up to like 200 kilometers or so, and with a vertical resolution of around 20 kilometers. Okay, so the current global helioseismology cannot reach that much precision. And then we can also learn about where are the origin of these sources. Are they mostly shallow or are they mostly deep, right? If they have any specific structure in their statistics. And there is a long-standing problem in the acoustic spectrum of the P modes that we call the acoustic line asymmetry problem. And that problem says that if you look at the ridges of the P mode, you will see that there is more power in the lower frequency compared to the higher one. So there is not much explanation, and there is some theoretical analysis that says that this must depend on the spatial distribution of the acoustic sources through height, right? So if we can find these individual sources, if we can develop their statistics, we should be able to answer that question too. And then on the upper atmosphere, we should be able to follow and track these individual acoustic sources. We should be able to know that how they're depositing energy, how they're depositing heat into the upper atmosphere. And we can also learn that how the upper atmosphere's heating frequency has any correlation with the lower atmosphere, which means the photosphere and the upper convection zone. So this is what we have been doing in the last couple of years in preparation of the DKIST observation. So I'm very happy to tell you at this moment that we have seen that using DKIST data, we can actually do all of these analysis. So we have some very preliminary results that all of these are actually viable, right? Using DKIST. And so here are my collaborators. So the acoustic source algorithm development, this was mostly done with Dr. Mark Rust. The spectral analysis was mostly done with Dr. Ivan Milic. And for the neural network, I have been working with Dr. Inouye Tremblay. For the data of the DKIST, I have been working with Dr. Yasirina Crisoli and Dr. Sadikov. And we have been also working with some polar images of the sun with Dr. Yeshudong. And I am immensely thankful to NSF and the National Solar Observatory for funding me through the DKIST Ambassador Program. And I'm also grateful to University of Colorado Boulder to give me the space and the means to do all of this research. So thank you so much.
Thank you for that. Great. Do you have any questions? Oh, Tay's hands are shot straight up. Go on, Tay.
Hi.
Yes. Hello.
The depth profile
Mm-hmm.
is based on the phase velocity observations, right?
Yes. Yes.
Relying on the stratification, like solar atmosphere.
Yes.
Does it assume? I'm assuming we don't have the actual profile of the solar atmosphere. Do we just assume linear stratification?
Yeah. For now, I have taken a mean muram that is like a second order a polynomial change, right? And then during our inversion, it will add a perturbation on top of that.
Okay.
Yeah.
Yeah. I was just curious if there's any other reason to assume. There's any reason to not assume it's like something.
Yeah. So you can also assume linear, but for now, I mean, what we have seen so far using the global helioseismology and also from the solar box simulation and the medium simulation, we have some sort of an understanding that how it should look like. So it should so what we should expect is the sound speed would go down almost linearly, and the velocity is supposed to go down following as a second order polynomial. So that is what we have assumed. But I think in the future we can be more sophisticated, and we should be able to be less reliable to the models and try to incorporate more realistic measurement.
Right. Thank you.
Sure.
I guess following on then from Tay's question, with the DKIST improvement in resolution, how much deeper can we go? Do we have a sort of number on mapping the convection zone?
Sorry, can you repeat again? I got.
With the improvement in the resolution of the DKIST,
Yes.
we have like an initial sort of guess or idea about how much deeper we can go with mapping.
Yeah, so I think so using global helioseismology, we have been able to map like really, really deep, right? But the problem is that we didn't have very high resolution. But what we have done over here, this is more like a local helioseismology. And with this technique, we can observe the sun, at least so far what we have found, with a horizontal spatial resolution of 400 kilometers, 200 to 400 kilometers. So which means half an arc second, or even smaller than that, 1/3 of arc second. And in terms of depth, we should be able to see up to like 200 to 300 kilometers. That means the upper convection zone. And this is actually very interesting because before flare, we know that there should be a flux tube emergence. So if you have a flux tube that is coming through the photosphere, you should be able to predict it long before it would appear, in the corona, right? Because if you have a really thick flux tube, then when all of these acoustic sources, they will come out, you will find that there is a specific signature that there is a region of a strong magnetic field, right? So you can use this information to actually find out that if there is a flux tube that is coming out, and what is the field strength of the flux tube, right? So I think this would also enable you to do better a prediction for your flares in future.
Great, thank you. Yeah, as we have a question in the back of the room.
When you go from the photosphere to the chromosphere, or from the chromosphere to the corona,
Mhm.
have dramatic changes in temperature and the sound speed,
Yes.
that should emerge as some sort of reflection or refraction at those surfaces. Do you see those? Do you see any of those effects? You know, when you go from the photosphere to the chromosphere. Or the higher-
Yes. Yes, you're absolutely right. So we have seen evidence of a reflection and a refraction in the chromosphere in the Muram simulation. Now, when we have made the observation with the very recent observation, we think we have seen this evidence of a reflection, but we are still not sure. We need to do a wavelet analysis and other stuff, because when we are doing the real observation, it is very difficult to analyze it in terms of height, right? So in order to see if there is a reflection or a refraction when you're going through height, it is a little bit still more difficult, right? So you need to have the whole spectrum and everything. But in the simulation, we have seen this. We have seen that when you have a strong magnetic canopy, we have seen that our acoustic sources, they are actually getting sidetracked or refracted.
How does that? Do you have any idea how that would affect transmission coefficient or power?
No, that is what we are trying to understand right now, that we are trying to quantify those. And to be honest, if we want to do it properly, we shouldn't do it in the Muram, because Muram is extremely good for a photosphere, but when it comes to a chromosphere, we need to use something better, which is like a mancha simulation or a Bifrost. So we are having a collaboration with those teams. And as soon as we have some data, we would be able to do it more efficiently. And we should be able to tell that how much your transmission efficiency is happening, or how it is dependent on ionization or other variables.
Do you have any final questions? If not, I think we should thank Shah again.
Thank you so much for inviting me.
Thank you very much.